a deeper explanation of quantum physics. Welcome to our in-depth journey into quantum physics. In this video series, we'll explore the history, main theories, and real-life examples that show how quantum physics shapes our world. We'll break things down step by step, using simple examples so that everyone can understand this fascinating subject that governs the very building blocks of our universe. Quantum physics might seem like something only scientists in laboratories need to worry about, but the truth is that it affects every aspect of our daily lives. From the smartphone in your pocket to the solar panels on rooftops, quantum physics is the invisible force that makes modern technology possible. Today, we're going to take you on a journey through this incredible world, starting from its mysterious beginnings over a century ago. Part 1: The birth of quantum physics. The problem with old physics. In the late 1800s, scientists felt confident that they understood how the world worked. They used what we now call classical physics to explain how things move and interact. These laws, developed by brilliant minds like Newton, seemed to work perfectly for everything from falling apples to orbiting planets. Scientists thought they had figured out the fundamental rules of the universe. But then something strange happened. Some experiments started giving results that didn't fit the old rules at all. It was as if nature was playing by a completely different set of rules that nobody understood. 3 particular experiments really puzzled scientists and changed everything we thought we knew about the world. The first mystery was called blackbody radiation. When scientists heated objects until they glowed, the colors and brightness they saw didn't match what classical physics predicted. According to the old theories, hot objects should have been much brighter than they actually were. It was like nature was refusing to follow the rules that had worked so well for everything else. The second puzzle was the photoelectric effect. Scientists discovered that when they shone light on certain metals, electrons would fly off the surface. But here's the strange part. The energy of these electrons didn't depend on how bright the light was, but on what color it was. This made no sense according to classical physics, which said that brighter light should always give more energy to the electrons. The solution: new ideas. Faced with these mysterious results, brilliant scientists began to propose radical new ideas that would completely change our understanding of the universe. These ideas seemed crazy at first, but they perfectly explained the strange experimental results that classical physics couldn't handle. Max Planck was the first to suggest something revolutionary in 1900. He proposed that energy doesn't come in a smooth, continuous flow like water from a tap. Instead, he suggested that energy comes in small, fixed chunks that he called quanta. It was like saying that instead of being able to pour any amount of water you want, you can only pour it in specific, predetermined amounts. This idea seemed bizarre, but it perfectly explained the blackbody radiation problem. Albert Einstein took this idea even further in 1905. He showed that light itself is made of tiny particles called photons, not just waves as everyone had believed. This was shocking because scientists had proven that light behaves like waves in many experiments. Einstein's explanation of the photoelectric effect using these light particles earned him the Nobel Prize and helped establish quantum physics as a real science. Niels Bohr then revolutionized our understanding of atoms. He explained that electrons don't orbit the nucleus like planets around the sun, as scientists had imagined. Instead, electrons can only exist in specific, fixed orbits with certain energy levels. They can jump from one orbit to another, but they can never exist in between these allowed positions. It was like having a staircase where you can stand on any step, but never float between steps. Werner Heisenberg and Erwin Schrödinger developed the mathematical framework that could describe these quantum systems. Their work gave scientists the tools to calculate and predict quantum behavior, even though that behavior seemed to contradict everything we experience in our everyday lives. Part 2: The main theories of quantum physics. Quantization. And the foundation of quantum physics is the idea that energy, light, and matter come in fixed, tiny amounts called quanta. This concept is called quantization, and it's completely different from our everyday experience where things seem to change smoothly and continuously. To understand quantization, imagine electrons in an atom. These electrons can only have certain specific energy levels, like steps on a ladder. An electron can be on the first step, the second step, or the third step, but it can never be halfway between steps. When an electron moves from a higher step to a lower step, it releases energy in the form of light. When it moves from a lower step to a higher step, it must absorb exactly the right amount of energy to make that jump. This quantization explains why different elements produce different colors when heated. Each element has its own unique set of energy levels, like its own custom staircase. When electrons jump between these levels, they produce light of specific colors that act like a fingerprint for that element. To wave-particle duality, one of the most mind-bending aspects of quantum physics is that tiny particles can act like both particles and waves at the same time. This concept is called wave-particle duality, and it challenges our basic understanding of what things really are. The most famous demonstration of this is the double-slit experiment. When you shine light through two small slits onto a screen, you see a pattern of bright and dark bands, just like what happens when water waves pass through two openings and interfere with each other. This proves that light behaves like a wave. But here's where it gets strange. If you look very closely at the screen, you'll see that the light actually arrives as individual photons, one at a time, like tiny particles hitting the screen. Even more bizarre, if you try to watch which slit each photon goes through, the wave pattern disappears and the photons start behaving like simple particles. It's as if the act of observing changes the fundamental nature of what light is. This wave-particle duality isn't just true for light. Electrons, atoms, and even larger objects all exhibit this strange behavior. They can act like waves when nobody is looking, but behave like particles when measured or observed. Superposition. Perhaps the strangest concept in quantum physics is superposition. This principle states that a quantum object can be in many different states at the same time until someone measures it. It's like a coin that is spinning in the air. Until it lands, it's neither heads nor tails, but somehow both at once. Schrödinger created a famous thought experiment to illustrate how weird this concept is. He imagined a cat in a box with a device that might kill the cat based on a quantum event. According to quantum physics, until you open the box to look, the cat is both alive and dead at the same time. This seems impossible in our everyday world, but it's exactly what happens with quantum particles. In real experiments, scientists have shown that electrons can indeed be into places at once, spinning into directions simultaneously, or existing in multiple energy states at the same time. This superposition only collapses into a single state when the particle is measured or observed. Uncertainty principle. The uncertainty principle, discovered by Werner Heisenberg, tells us that there are fundamental limits to what we can know about quantum particles. You cannot know everything about a quantum particle at the same time, no matter how good your measuring equipment is. The most famous example involves position and momentum. If you know exactly where an electron is located, you cannot know exactly how fast it's moving or in which direction. Conversely, if you know precisely how fast an electron is moving, you cannot know exactly where it is. This isn't because our instruments aren't good enough, it's a fundamental property of nature itself. This uncertainty isn't just a technical limitation, it's built into the fabric of reality. The more precisely you try to measure one property of a particle, the more uncertain its other properties become. This principle has profound implications for how we understand the world at its most fundamental level. Entanglement. Quantum entanglement is perhaps the most mysterious aspect of quantum physics. It describes a phenomenon where two or more particles become connected in such a way that what happens to one particle instantly affects the other, no matter how far apart they are. When two electrons become entangled, they share a quantum connection that transcends space and time. If you measure one electron and find it spinning in one direction, you instantly know that the other electron will be spinning in the opposite direction, even if it's on the other side of the galaxy. This connection happens faster than the speed of light, which Einstein famously called spooky action at a distance. Scientists have tested entanglement in countless experiments, and it always works exactly as quantum physics predicts. This phenomenon is now being used to develop new technologies, like quantum computers and quantum communication systems. Thank you for watching part 1 and part 2 of Explanation of Quantum Physics. Give us a like if this video was knowledgeable and interesting. Subscribe and stay tuned for the next parts of the explanation about quantum physics. Next video, Part 3, the mathematics of quantum physics, and Part 4, simple examples of quantum physics.